Good morning. It's Thursday, May the 11th, 2017, and I've been wanting to shoot another video on the energy flows in my Ford C Max Energi plug-in electric vehicle. And instead of showing you numbers or spouting numbers to you, I've been wanting to do a visual representation of how much energy the electric motor in this vehicle needs roughly to drive the vehicle 1 mile. And what I had worked out previously is that over 1,000 miles the electric motor used about 1 million BTUs, and the internal combustion engine requires 3.3 million BTUs to drive this vehicle about 1,000 miles. This exact ratio is like 3.36. So and I'm an old boiler man, so retired from 20 some years of operating boilers and jet turbines and so forth. So it occurred to me that the amount of energy could be demonstrated by heating water, and it turns out that it only requires about 1,000 BTUs to drive this car 1 mile in electric drive. And so, since the definition of a BTU is the amount of energy required to heat 1 pound of water 1 degree, I decided to take 10 pounds of water, which I'd only have to heat 100 degrees. So I had to do a little bit of mathematics. There's 8.34 pounds of water in 1 gallon, and it turns out I needed 153.4 some ounces of water to equal 10 pounds. And so I've put 10 pounds of water into a pot in the kitchen on the stove, and we're going to boil it. And the temperature of the water, the starting temperature, is about 102 degrees. And because I live at 4,000 feet, I only need to get it up to about 203 degrees for it to boil. And so that'll be the end point of the experiment, is after watching the pot boil and watching the clock, we'll have demonstrated the amount of energy that it requires my Ford C Max to go 1 mile. So we're going to go in the kitchen now, and we're going to look at boiling some water. So here we are at the stove, and there's the pot. I've already got the water in it. And the way I did it was I used this measuring cup, which is graduated to 32 ounces. I put 4 of them in it, and I had to put 25.47 something ounces more water to equal 10 pounds. Now I've already got the temperature of the water up to 100 plus degrees. And you're basically just going to have to take my word for it. I can't find a big thermometer. But anyway, this thing says roughly 100 degrees. And so we're going to start it right away. And this is a pretty big burner on this stove. It produces about 13,000 BTUs, I think. And there is our clock on the wall over here, and it's saying it's 12:35. So now again, as I indicated in the garage, 1 BTU will raise 1 pound of water, 1 degree Fahrenheit. So 10 BTUs will raise 10 pounds of water 1 degree Fahrenheit. I have 10 pounds of water here, and I need to raise it 100 degrees, so I need 1000 BTUs. And the experiment is designed to show an endpoint where you won't have to look at a thermometer. The water will simply be boiling. So we're going to have to hit the pause button here. Keep looking at the clock, and I'm not going to make you watch water boil until it reaches water heat until it reaches the boiling point. But again, as I indicated in the garage, the internal combustion engine requires 3.36 times the amount of energy that the electric motor requires to drive the car 1 mile or 100 miles or 1,000 miles or whatever. So to do this same experiment, to show you the energy required to drive the internal combustion engine 1 mile, we would have to have 33.6 pounds of water. So just imagine at least 3 of these kettles, plus another third, heating on the stove to do the same amount of work. And the reason for that is most of the heat energy in the internal combustion engines lost as heat to the environment out the tailpipe due to friction and so forth. And internal combustion engines are only no more than 30% thermally efficient. Usually modern cars are around 25, and they also require a transmission, which is which an electric motor does not require. And electric motors are about 90% efficient as a drive unit for a car. So there's a big difference, and this is what we're trying to demonstrate right here. So there's our water, and there's our clock. So we're going to pause now, and I'm going to come back when we're closer to boiling this water. Here we are. We've only gotten the pot up to about 136 degrees, which would take a while to show that. But what I wanted to point out here is that the transmission in my truck has to get up to 136 degrees internally before the truck is really not losing a lot of energy to friction in the transmission. So when I'm trying to do an MPG run on my pickup truck, I never really start until I allow the transmission to get up to 136 degrees. So we've been trying to boil this water now for about 5 minutes, and I finally got it up to 135 degrees or so. So this gives you an idea of just how warm the transmission in an internal combustion engine needs to get for it to be operating efficiently. Okay, we're back, and now we have a little over 15 minutes have elapsed, and I have the water at about 180 to 190 degrees. So let's see, 5, 10, 15, 17 minutes or so. My best calculations are telling me that it should take no more than 20 minutes. What you run into when you try to boil water is defeating surface tension. When you're reaching the boiling point of water, the surface tension literally causes the water to rise. We have that phenomenon in boilers. The water will literally lift up in the drum head before it breaks into a boil. And that's the surface tension that's holding it back. And but all we're concerned about here is the total amount of energy required to heat that water, 1,000 BTUs, 100 degrees. And we're not really concerned about the amount of heat that's escaping around the sides of the pan or going in to heat the pan. by definition 1000 BTUs is going to be heating this water 100 degrees. And the rest is waste heat to the room or to the pan or whatever. And that's not a major concern of ours. So, and a couple hundred degrees is where my transmission in my truck I was telling you about operates efficiently, about 198 or so. So we're not up to 190 yet. We're getting there. So I'm going to hit the pause button again. So here we go. Here we are. You're beginning to see bubbles coming off the bottom. We still haven't got a boil going just yet. But we're at around 200 degrees. And 20 minutes. So this is pretty much the end of our experiment. I hope you can see the bubbles. This water is definitely trying to boil. You might also see some vapor coming off of it too. It's kind of hard to hold this thermometer over this. It's very hot. Yeah, I'm showing 202. So it's trying to get there. We're definitely reaching a rapid boil. There it goes. See it? So I'm going to pause it here and resume in the garage. We definitely have some hot water. 10 pounds of it, 1,000 BTUs. So here I go. I want to shut the fire off. And there's our time check right there. So I'm going to hit the pause button. We're going to resume out in the garage. So there we have it. That was the amount of energy required to drive this car 1 mile. And that includes my charging losses. In other words, about only 82% of the energy I get out of the line circuit here goes into the battery in this car, which is pretty good. It's better than 120 volts, which is only 72%. So, and all that is coming off of those solar panels out there. You can see them just under the canopy of that tractor. So this is the major point I've been trying to get across in some of my videos, is generically it's about electric cars. So electric drive is over 3 times more efficient than an comparable internal combustion engine, and it's the wave of the future. And some of these labs out there now are starting to talk about battery packs of the same size, weight, and density and so forth that's currently in 300-mile range cars, 250-mile range cars, and so forth, that could get 600 miles of range in an electric car. And I think these are coming in the next few years. So this is where we're headed, and there's really no stopping it. So it needs market pull, so I'd get on board. If you're thinking about buying an electric car, I definitely would do it. I've got to close this down. I can't go over 15 minutes. So I'm going to post this now. Talk to you later. Bye.